Hello everyone, Dr. Jenkins here. We just met last night talking about, among other things, the parts of the cell, ways in which we move things into and out of the cell through diffusion, osmosis, and active transport. But at the very end, we began talking about the resting membrane potential. And I know it was a long night, and we covered some of the hardest stuff at the end. So what I wanted us to do is I wanted to record a little video and go through this again. That way you can have a nice little study tool to help you going over this very important part of the lecture. All right, so here we go. If you remember, we talked about the cell, and pardon my bad drawing, although I suppose now you're used to it, even after a couple lectures. And, there's going to be an inside of the cell, and there's going to be an outside of the cell. And just as a reminder, our cell membrane up close is made up of a phospholipid bilayer. You remember that? So the heads face the inside and the outside, and the heads are hydrophilic. They like water, and the tails are in the middle, and the tails are hydrophobic. They don't like water, so that prevents water from accumulating in the inside of the plasma membrane. And these phospholipids go all the way around, but I'm not going to draw them all the way around just to save myself some time. And of course, we remember that intermixed among the phospholipid bilayer are these protein channels. And one big function of these protein channels is that they act to transport things in and out of the cell. Excellent. Now, let's start talking about the resting membrane potential. So when I introduced this last night, I introduced it in a particular order on purpose because I wanted to purposely build the knowledge in a logical way. So the first thing that is probably best to understand is just to define what a resting membrane potential is. What we're referring to is at rest, when a cell isn't doing anything, the inside of the cell has a negative charge relative to the outside. So the best example of this would probably be a nerve cell. We know what a nerve cell looks like, right? Kind of looks like a kite and has a long axon. Yeah? Well, the inside of a nerve cell, or any cell, is negative compared to the outside. And we're talking about this at rest. So at rest, when a nerve cell isn't even doing anything, this nerve cell is not conducting a nerve impulse, it's just at rest. At rest, cells have a negative charge on the inside. And this negative charge is a form of potential energy. Even though this nerve cell at rest isn't doing anything, the fact that it has that charge at rest is a form of potential energy. And I gave the example in class of a battery. That's a really bad battery. There's my battery. A battery, when you just hold it in your hand, doesn't do anything. Yet, that battery contains potential energy. And because the cell and because the battery contains potential energy, when we put that battery in a certain situation, it can create something for us. We can put it into a flashlight and it can create light. And this works the same way for the nerve cell. Even though at rest it's not doing anything, it has that potential energy. And because it has potential energy, when we want it to, we can manipulate that potential energy and create something. In this case, we can create a nerve impulse, which is an electrical current. All right, great. So number one here is just being able to define what the resting membrane potential is. Okay, the resting membrane, just to review, the resting membrane states that cells have a negative charge on the inside compared to the outside at rest. So the cell's not doing anything, but it contains a negative charge at rest on the inside. And this is a form of potential energy that we can later use to convert into actual energy, like when a neuron conducts a nerve impulse. All right. The next thing to talk about is how we generate that resting membrane potential. Ooh, excuse me, didn't mean to do that. Let's go back here. Okay, so our number 2 thing to talk about is how we generate that negative charge. And we generate this negative charge based off of the movement of ions. So the inside of the cell is always going to have more potassium ions than the outside of the cell. The outside of the cell is always going to have more sodium ions. Okay? Inside of the cell has more potassium, outside of the cell has more sodium. Now, there will be a little bit of sodium on the inside, and there will be a little bit of potassium on the outside, but there's always going to be more potassium on the inside and more sodium on the outside. And as we're going to find out, it is the movement of these ions that generates this negative charge at rest. And what we're going to find out later this semester is when we manipulate these ions even more, that's how we generate a nerve impulse. So it's all about the ions, baby. Okay, so what's going to happen to these ions? Well, these ions are going to diffuse from high to low concentration. And these ions happen to diffuse through a protein channel. So for example, potassium will diffuse from high amounts inside the cell to low amounts outside the cell. And then sodium will diffuse from higher amounts outside the cell to lower amounts inside the cell. Perfect. This is diffusion, movement from high to low through a semipermeable membrane. And I want to point out again that these ions mostly diffuse through protein channels, and they diffuse through their own protein channels. So potassium will diffuse through its own protein channel, and sodium will diffuse through a different protein channel. But here's the thing. How do we generate a negative charge on the inside when we're talking about 2 positive ions? And the answer is because potassium diffuses faster than sodium. Much faster, 50 to 100 times faster. So as I did in class, let me lay out some numbers just to make sense of this. And these are made up numbers, but it helps us understand what we're talking about. Let's say that in every 1 millisecond, 10 potassium ions leave the cell. So from the perspective of the inside of the cell, in that 1 millisecond, the inside of the cell loses 10 positive ions. In that same 1 millisecond, maybe only 3 sodium diffuse in, right? Because potassium diffuses out much faster than sodium comes in. So in that 1 millisecond, the inside of the cell has lost 10 positive ions, and it's only gained back 3 positive ions. So if I do the math from the perspective of the inside of the cell, what is the resulting charge? -7. So that's how the inside of the cell becomes more negative compared to the outside. And I wanted to point out again, like I did in class last night, I think I have to sneeze. Hold on for a moment. Excuse me. I felt the second one coming on, just had to wait, pardon me. So this difference in charge is only right around the cell membrane. It is not on the inside of the cell, so there is no resting charge towards the inside. It's only around the cell membrane, and it is a relative charge. The inside is negative relative to the outside. And like I said, even though we're talking about positive ions, this happens because potassium flows out faster than sodium flows in. I'm so sorry, everyone. I apologize. Okay, so that's how we develop the negative charge on the inside. Potassium flows out much faster than sodium flows back in, so the inside is more negative relative to the outside. That's pretty cool. And then, excuse me, we talked about one last thing. So let's clear this out so we can better understand. We'll remove the 10 and the 3. Okay. The last thing we talked about had to deal with the sodium-potassium pump. All right, so if we let this passive diffusion continue, if we just let potassium continue to flow out of the cell, and if we let sodium continue to flow into the cell, eventually they would even out. The body would find some way to maintain homeostasis, because your body doesn't want different. So it would find a way to even out the charges. Maybe it would close more potassium channels, and it would find a way to even out the charge. Because that's what the body does, right? The body is so good at homeostasis. If we just let this happen just with passive diffusion, the body would find a way to maintain homeostasis and there would be no charge. But that's bad. We talked about it. We actually need a difference here because it is that potential energy or difference in charge that allows us to create a nerve impulse. So if we didn't have this difference in charge, we would not be able to make a nerve impulse, and that would be bad. So here's a situation where we actually don't want homeostasis. We want the inside of the cell to be more negative compared to the outside. So in order to make sure that we don't maintain homeostasis and remove that charge, we have to enact something called the sodium-potassium pump. And the goal of the sodium-potassium pump is to maintain the original concentration gradients. Of the ions. Because if we didn't maintain these original concentration gradients, and we didn't let potassium flow out faster than sodium comes in, then we would lose that difference in charge. Okay, so we need to have the sodium-potassium pump to make sure that we're always maintaining the original concentration gradients. Go back to our previous step. How is it that we develop this resting charge? Because potassium flows out faster than sodium flows in. So the only way we can do that is if we make sure there's always more potassium on the inside and there's always more sodium on the outside. Okay, and I'm going to add another note here. Another function of the sodium-potassium pump, give myself more space here. Another function of the sodium-potassium pump is to avoid, or I guess prevent is a better way to put it. Let me change words here. Prevent body from finding homeostasis. which here, homeostasis would mean no charge. Right? So usually we like homeostasis, but here we don't because we want the inside of the cell to be more negative compared to the outside. And how do we ensure that we can maintain that difference in charge? By maintaining the original concentration gradients. And we do that by the sodium-potassium pump. So, here we go. At another channel, at the same time as potassium and sodium are doing their passive diffusion, on another channel, we have the sodium-potassium pump. And what's happening is, for every 1 ATP, we pump 2 potassium into the cell, and we pump 3 sodium out. So for every 1 ATP energy molecule, this pump continuously pumps 2 potassium in, 3 sodium out. And what are we doing? By pumping potassium in, we're maintaining our original concentration gradient, where there's more potassium on the inside. By pumping sodium out, we are maintaining our original concentration gradient, where there's always more sodium on the outside. Why does this require ATP? Because we're moving against the concentration gradient. So here, we're pumping potassium from low to high. And in order to move something against the concentration gradient, we need energy. I've put a link to the YouTube video that I showed you in lecture that shows this pump operating. You need to know the specific numbers. Pumps 3 sodium out, 2 potassium in per 1 ATP molecule. Why is it that the numbers are different? Why is it 2 potassium and 3 sodium? Because this further helps us maintain negative on the inside, positive on the outside. By pumping only 2 positive in, but 3 sodium out, we're pumping more positive out. It helps the outside stay more positive relative to the inside, which is actually what we want. All right, folks, feel free to watch this again and again. I hope it helps. If you have any questions, let me know.